eigenvalue problem. I will show very soon in the next half an hour why this kind of problem is very important, not only for physics, but also for mathematicians. Okay, so A times A equal to lambda times I say the point is a matrix times the eigenvector usually produce another another vector. However, if this column vector is eigenvector, then A times its eigenvector will produce the same vector in the same direction. That's why it is called lambda. Because on the right-hand side, it is lambda times A. So it is actually the same vector as A, just reduced in length or lengthened by a number lambda. Okay? Therefore, this kind of problem is called eigenvalue problem, and the A eigenvector, lambda eigenvalue. And here I'm going to solve this eigenvalue problem, and the procedure is general. However, this procedure is just what we have already did in the beginning. Yeah. A times A equal to lambda over A. Where does that come from? In our class, it's from the couple equation, right? Or the couple oscillation. In the beginning of the last class, I review how we, from here, plug in the solution, we arrive at this. 记不记得？你要再看一次吗？
可是你为什么可以要怎么讲？就是你怎么知道那个那个地方就是 eigen？
哦，就是 eigenvalue 在。
对啊。
没有 omega square is just一个 number. I could call it omega square. I could call it lambda. OK.
lambda 是 eigenvalue。
对 ，lambda 是，所以应该是 omega square 是 eigenvalue。
对啊，可是你是把这个公式跟大 A 乘小 a 等于 lambda 乘 a 做比较，然后才知道 omega 平方是 lambda， 这样吗？
对，可是 omega 我可以叫它 omega square， 我也可以叫它 lambda square， 它只是一个数啊，我怎么叫它并不重要。
说你怎么知道这公式怎么来的？
哪一个公式？
就现在指的
这个。就是这样子来的、啊。就是你把这个是你的那个 equation of motion 啊，你假设你的解是长这样，啊，你把它带进去，不就得到这个吗？对吧？就上一节课，我可以再秀一次给你看。在上一节课，我们一开始的 review 就是在 review 这件事情啊。假设，来，我们回到上一节课的一开始的地方，有没有？这一页。哦，那时候当然我们叫 S 啦 ，notation 有一点不一样啊。对呀，啊。没错，好，我把这个 A 把它带进去这个 equation， 那我就得到了 S 减掉 omega 平方 I 乘上 A， 我就得到了 S 乘上 A 等于 omega square 乘上 A。那只是我们现在用 A 的大 A 的这个符号 instead of S， 但是就是一样的。或许我应该用，Sorry for flipping around。对，就是这个。这页更清楚。我们上一节课开始的 review 是从这里开始的。I assume the solution is this, and then I plug it into the equation, and then simplify that, and becomes A times A equal to omega squared times A. I still don't know what omega is, but this is equation for A. 就是这样来的。If I can solve omega squared, I can solve A, then I can solve the equation of motion. That's one example of how to use it. However, I'm going to use it to show you how the mathematicians use it. This is how physicists use it. Okay. However, it's just a mathematical problem. This mathematical problem is a matrix times A, could it be possible equals a number times A itself? It's a mathematical question. It's a mathematical question. 好，这是一个数学问题。我就是一开始就问，那我有没有可能有这样子的一个可能性？一个矩阵乘上 A 等于一个数乘上 A。不要忘记了，我刚刚已经秀给你看。At the end of this class, I just showed you. In most cases, in general, when you multiply a matrix by a column, it becomes another column. So original column vector times A, it becomes another vector. Usually that's the case. 这是通常的这个情况 is in general. Okay. However, for a certain direction, the result will be in the same direction as the original. These are rare. That's my point. These are rare. That's the general case. And these are rare, so why don't you just write it down and solve it? And I will show you, of course, I will show you why it is important, this question. When you find these kind of solution, it is important for mathematically, and it is important physically. 在物理上很重要，因为它就是你在解 couple oscillation 的时候的震荡解法。那数学上这样的解为什么重要？等一下你就会知道。好，等一下你就会知道。But anyway, it's a fun question. It's a fun question. Okay, A times A equal to lambda A. Okay, eigenvalue problem. And the procedure, you have already seen it at least 3 times. Okay, so I do not repeat every step, but the procedure is general. Okay, the key step is to pull the right hand side to the left hand side and simplify it into A times lambda 1. I is the identity matrix, as people asked already. It is 1, 0, 0, 1. Okay, so this A minus lambda I, this matrix times A equal to 0. As I showed you several times already, if this A minus lambda I has an inverse, then the vector A could only have one solution, that is 0, 0, which we are not interested in. Okay, so here I write it. A, if this inverse matrix exists, then A could be only equal to 0. We are not interested in this kind of solution. Therefore, I wanted a condition so that this A minus lambda 1 has no inverse. The condition for this guy to have no inverse is that the determinant of it equal to 0. The reason is simple, because there is a very, very famous formula for the inverse matrix. You can check it from Afghan. The inverse of a matrix is equal to da 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 da. I don't care. But it is divided by determinant S. So for this to not exist, the only possibility is that determinant S equal to 0. Okay. So the logic step is very, very clear and simple. Again, only if the determinant of the matrix is equal to 0, then the inverse matrix does not exist. Okay. So the condition for A to have solution is A minus 1 determinant equal to 0. And let's take an example. For example, A equal to 0.3, A 0.3, 0.2, 0.7. And you can write down A minus lambda 1, which will be 0.A minus lambda 0.3, 0.2, 0.7 minus lambda. Is that okay with everybody? Because this 1 is the 1, 0, 0, 1. That's the matrix. When it multiply any vector will be equal to the vector itself. So it's almost like 1. So that's why it's called identity matrix. Okay, so A minus lambda I will be lambda. So we'll give a lambda to the upper left elements and give a minus lambda to the lower right element. So the determinant becomes this. And it is easy to write down the determinant. It will be equal to this times this minus this times this. Do it yourself. It is equal to lambda squared minus dot 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 plus 1/2. And it is easy to find two solutions for if this is equal to 0, lambda could equal to 1, or lambda could be equal to 1/2. Got two solutions. So that means there are two cases, two situations where this thing happened. After multiplication by a matrix, the vector remains the same. Only two possibilities. Lambda equal to 1, lambda equal to minus 1/2. Only in these two cases will this kind of thing happen. For the rest of the lambda, the upper diagram will happen. 好，所以呢，对，所以只有刚刚讲这两种情况才会是下面这个图。OK， 那刚讲了 lambda equal to 1， 所以呢，作用了以后，它会维持一样的长度，同一个方向。等一下你就会看到。啊，另外一个呢是1/2，所以就有点像这个图，它的长度呢就会变成原来的一半。OK， 那如果不是这两种情况的话，都会是上面来。
那个浪大等于1，所以就是写成1，然后负1。
没有负1啊。那等一下，等那个。
有上面减 a 之后 a， 就是有这一张图后面。
哎。
然后你说这个会只有这个1负1。
对啊。
那浪达等于1，它代表的是。
哦，浪达1来。
就是套用在情况也是。
好，如果 lambda 等于1的话呢，在情况在这里。当我们解完了以后 ，lambda 等于1的，它的这个 a1 呢是0.6、0.4。好，我画个图。所以0.6、0.4大概是0.6、0.4，大概是这样。好，所以乘以 a 了以后，完全一模一样啊。Oh, well, I'll write a diagram again. So this is for 1 and 0.6, 0.4. So originally, it is this. Times A is equal to itself because lambda is equal to 1. Okay? We are talking about the same matrix.
我懂。
You don't. Let's see. It's the same matrix? Yeah, let me see. Yeah, it's the same matrix. So we are talking about the same thing. Yeah, I write in different times, so I'm not sure where I'm talking about the same A, but it is. So for this kind of case, it is the second case. Okay. Then only two situations, but we only got the multiple, but we didn't have the A yet. 你还没有把这个 eigenvector 找到。We find the eigenvalue. From eigenvalue, I can find the eigenvector. That's the key. Okay, so eventually I want the eigenvector, not just the eigenvalue. Okay, so eigenvalue, if it is, there are two possibilities. One, let's call it lambda 1, which is equal to 1, and you just put in. So that's a standard procedure. We just plug in the lambda, the value of the lambda, into the equation itself. Don't forget that's the original equation. In the first page also. That's the original equation. What we have here is that this equation has solution only for lambda taking certain value, lambda 1 and lambda 2. So now we have lambda 1 and lambda 2. What we need to do is to plug in this original equation and then try to solve A1 and A2. OK, 好，所以呢，你自己一定要记得，这是我们的起点。当然，这个才是起点。那我只是把它移到左边去，这个就变成我们现在的起点。然后我的意思就是说，你这个 lambda 呢，只有在两个值的时候它才有解。好，那现在我就把它给解出来嘛。好，那就是我们的 eigenvector。OK， 好 ，then lambda 1 we plug in lambda equal to lambda 1 equal to 1, then the matrix becomes 0.8 minus 1, 0.7 minus 1. So this matrix becomes minus 0.2, minus 0.3, and minus 0.2 and minus 0.3. So if you expand this, it becomes 0.281 minus 0.382 equal to 0. Okay, it means A1 times 0.2 equal to A2 times 0.3. So I can say that we have already defined the eigenvector. The eigenvector, we only get the ratio of the two components, okay, because it is an equation like this. So I will choose the A1 to be 0.6, 0.4. Please observe that the ratio between them are just 0.3 over 0.2. You just plug in, and you can see clearly this choice will satisfy this equation. A minor comment, the other equation could also apply. There are two equations. It could be this times this equal to 0, or 0.2, 0 minus 4 times this also equal to 0. But you can see clearly they are the same. So on the paper, there are two equations. But in essence, there's only one. Actually, that's the result that the determinant is equal to 0. Okay, so only one equation. So this equation must have some solution. So it's 0.6, 0.4. So, and lambda is equal to 1. So that's why I say A acting on 0.4, 0.6, 0.4 will become itself with the same length. Second case, lambda equal to 1/2. I'll leave you to this exercise yourself. Then the matrix will become 0.8 minus 0.5. That's 1/2. And then it becomes 0.3, 0.3. 0.8 minus 0.5 is equal to 0.3. So the solution, 0.3 times A1 plus 0.3 times A2 equal to 0. Therefore, it gives you that A1 and A2. The ratio between them is 1 minus 1. Okay. You can do the second also. It's the same. Yeah.
为什么要找0.6跟0.4？可以写0.3跟0.4。
好高兴。Yeah, I choose the most convenient one. Of course, 你也可以选. You can also choose 0.3, 0.2, or 3, 2. Because I'm going to multiply by C1. So you can choose any C1, right? Okay, so it could be anything. The ratio between them are 3 over 2. 那我喜欢0.6、0.4. You can choose your own. Yeah, actually, it probably is most natural to choose 0.3, 0.2 instead of 0.4. Yeah, next year I will do 0.3, 0.2. Okay, yeah, good. Thank you. Okay, so I think it's clear for everybody. So the next page is our final result. The final result is A times A1. Here I use the index to signal it's the first set of eigenvector and eigenvalue. You can see already one eigenvalue produces one eigenvector. One eigenvalue produces A1 eigenvector. So there's one-to-one correspondence. Therefore, I use the index to signal lambda 1 corresponding to A1 upper index. Then it will become A times the first eigenvector is equal to eigenvalue 1 times the same eigenvector. Second eigenvector is 1/2. So A times the second set of eigenvector is equal to 1/2 times A2, 1 minus 1. That's the final result. So I will say for these two special cases, matrix multiplication is just a number product. Hope you understand the final words. Okay? Yeah, and here is a summary of the procedure from the textbook. I hope it's very, very standard, but it's important. So that's why I go it. I think that's the fourth time through the process. Through the process. 我们把这整个讲了4遍了哈，一定会考，保证。It will be on the final exam. Okay, so let me use the next 20 minutes to 30 minutes. Oh, of course, here I got, in order for you to familiar with yourself with the procedure, I try another matrix. This time it's a symmetric matrix. I won't go through it here, so please do the exercise at home. Here I choose S is 9, 3, 3, 1. So observe that it is symmetric. Using the simple the same procedure, I got lambda equal to lambda 1 equal to 0, or lambda 2 is equal to 10. These are the two eigenvalues. And I can keep on using exactly the same procedure to find the first eigenvector, the second eigenvector. It is 1, minus 3, and 3, 1. Did you observe that? These two are orthogonal. This is 1 minus 3, this is 3, 1. They're perpendicular to each other. If you take an inner product of them, it is 1 times 3 minus 3 times 1 equal to 0. They are perpendicular to each other. I will show you maybe next week, probably not this week. This is not a special case. Actually, the same kind of property apply to all symmetric matrices. 下礼拜我就会告诉你这件事情呢，并不是只有对这一个特例是对的 ，OK？ 所有的只要是 symmetric 的那个 matrix， 它的两个 eigenvector 彼此呢都是正交的，都是垂直的。你不觉得很奇怪吗？Whether a matrix is symmetric or not, it is related to the fact that their eigenvectors are perpendicular to each other. I can prove it very easily, not very hard. Maybe I can do it today. But anyway, this is a very significant theorem and very, very powerful theorem. Okay? Well, mathematics are miracles. Oh, mathematics are miracle. This is one of the miracles that is going to happen very soon. Okay, so symmetric matrix. Now I'm going to use two powerful and beautiful theorems to show you, to illustrate the utility of this eigenvector whole scheme of eigenvectors. The first, well, I will show you that eigenvector A of eigenvectors of the matrix A are also eigenvectors of A to the nth. A to the nth means A, the multiplication of n copies. A. This will define just like an ordinary complex, an ordinary variable. I will call it A to the nth. Okay, I use the same notation, A to the nth. Okay, and you know what? Actually, A is also an eigenvector of A to the nth with the eigenvalue lambda to the nth. You don't believe it? Let me show you. Actually, it's very simple. Now, let's multiply A to the nth to A. Don't forget, A is the eigen. Just 1 minute. I run out of power, so just a minute. Okay, so let me try. I multiply A to the nth matrix to the eigenvector. I can separate this A to the nth into two parts. A to the n minus 1 times A. I think it's okay with everybody. But now, if I isolate one from the rest of the A, this A can act on this A. This capital A can act on this small a on its own. Then A times A will be equal to lambda A. After all, the small a is the eigenvector of the capital A, right? Therefore, it will be lambda times A. Remember, lambda is just a number, so it can penetrate the matrix multiplication. So I can pull this number number lambda to the front instead of inside. Okay, so this will be equal to lambda times A to the minus 1 times small a. And then I can do it again. A to the n minus 1 could be separated into a to the n minus 2 times a. Again, the a is exposed to a again. The small a is exposed to the capital A, and the capital A will produce another lambda. So now 2 lambda. So lambda, lambda. Again, lambda could be pulled into the front, becomes lambda squared. So I use the 2a to produce 2 lambda. And I can repeat the process again, again, and again, until all the a are used, right? So it's so simple. Then, therefore, I got, when you finished all the capital A, you got lambda to the nth. Is that clear to everybody? So it's so simple. The result is quite clear. The small a is also the small a is also an eigenvector of a to the nth with the eigenvalue lambda to the nth. Okay. Then theorem 2. Theorem 2. All the vectors could be written as a linear combination of eigenvalue a1 and eigenvalue a2. Eigenvector a1 and eigenvector a2. Yeah, because there are 2 different, usually perpendicular vectors. Okay, so they could become a basis of the space, the unit vector. 就好像你在二度空 almost like the x-axis and y-axis in the ordinary 2-dimensional space. Therefore, I claim, I will prove later, maybe prove next week, okay, but believe me, any vector x could be written as the linear combination of a1 and a2. Let's call the coefficient c1 coefficient c2. So this x will be equal to c1 a1 plus c2 a2. Give you an example. Remember the eigenvector we have 0.6, 0.4, and 0.1 minus 0.1. I can decompose any vector. For example, here I take 0.8 and 0.2 as our example. It can be easily decomposed into this, the first eigenvector, plus 2 times this second eigenvector. Okay? So, 这件事情永远可以做得到。In Chinese, 一个航向量永远可以写成2个本征向量的线性组合。Remember it, it will be very, very important, but I'll prove it next week. Okay? Now, with this theorem, then a to the nth on any vector could be easily written down. For example, let's start with a to the first order. If you multiply a with x, then I told you already, x can be decomposed into c1 a1 plus c2 a2. Okay, and then the number and the a, because it's linear, so it could act on the first plus acting on the second. So it will be equal to a times this plus a times this. Again, because c1 and c2 are numbers, so they can be pulled out to the front. Therefore, it is equal to c1 a1 plus c2 a2. And a1 is equal to lambda a1 because a1 is the eigenvector. a2 is equal to lambda 2 a2. So the final result, a times any vector will be equal to the first eigenvalue times c1 times the eigenvector plus the second eigenvalue times c2 times the second eigenvector. So the simple result showed you that actually I can use this kind of decomposition to represent any matrix. Okay, you don't need to tell me about this matrix. This matrix is 0.8, 0.3, 0.2, 0.7, but you don't need to tell me the matrix itself. As long as you tell me the eigenvector, you tell me the eigenvalue. And I can show you, I can decompose any vector into the combination. And then I can get the result, A times X, directly from the calculation. In Chinese, 如果你告诉我并不需要知道 A 是多少，你只要我告诉我它的这个A 呢，它有两个 eigenvector， 这两个 eigenvector 的 eigenvalue 是多少？你只要告诉我，然后我就可以把我的这个 x 呢分解成它们两个的线性组合。所以你不用告诉我这个矩阵是谁，这个矩阵乘在任何的一个向量上面，它的结果我就立刻知道了。That's the key of this observation. A times x. You don't need to tell me about the matrix A. As long as I know A1, as long as I know A2, as long as I know lambda 1, lambda 2, and the C1 and C2, I got the result of AX. You don't need to tell me capital A. So that's why I would say the information in the eigenvector alone, our specific matrix could represent the matrix. That's why eigenvector and eigenvalue are important. Because all the information of matrix is stored in eigenvector and eigenvalues. Well, you may say that, why do I need this kind of calculation? Because I know the matrix, I can do the multiplication myself, right? But try this. How about if I want to multiply A to the 100? Could you do that? No, because you need to multiply A 100 times. A. You don't know how to calculate it. But let me show you how to calculate it. Because we already know that A to the nth times x. If this x could be decomposed into C1 A1 plus C2 A2, then I can multiply A to the nth directly on this A1, directly on this A2. But the first page showed you that A1 and A2 are also the eigenvector of A to the nth. Therefore, A to the nth times A1 is equal to lambda 1 to the nth. A to the nth to the A2 is equal to lambda 2 to the nth times A2. 算出来嘞。Okay, so A to the nth to the x times x is equal to C1 lambda 1 to the nth A1 plus C2 lambda 2 to the nth A2. It's complicated, it's abstract. Let me show you an example. For example, the x, any x, but they take this 0.8 and 0.2 as our example. As I showed you earlier, it could be decomposed into the combination of one eigenvector and the other. 这个0.8、0.2可以被分解成这个 eigenvector plus 2 times this eigenvector. That's okay, right? Now, if I want to multiply A to the 100 to x, you could not do it by hand, but now I can do it by this very, very powerful theorem. Remember, this to the 100, A to the 100 times 0.8, 0.2 is equal to A to the 100 times 0.6, 0.4, the first eigenvector, plus 2, that's the coefficient, A to the 100 times this. But I don't need to multiply explicitly this A to the 100 because I know the answer already. A, because this eigenvector is also an eigenvector of A to the 100 with eigenvalue 1 to the 100. For the second one, A to the 100 times this eigenvector will be equal to the eigenvalue to the 100. So it's 1/2 to the 100. 算完了。Yeah.
可是我们要怎么计算1/2的100次？
It's equal to 0. It's close to 0. That's a good question. Yeah, but 一个 number 的 100次总是比一个 matrix 的100次好算吧？Yeah, you can say that. Yeah, that's a good question. How do you compute a number's 100? But the point is, the numbers 100 to the 100 is much easier to calculate than the matrix to the 100.
那如果今天考试这样子，我到底要不要算出1/2的？
那我不会真的叫你算100嘛。考试的时候你放心啊，我有我的办法让你会写啊。好，但是你知道这样的 powerful 的地方吗？Especially in this case, 1/2 to the 100 is close to 0. So a to the 100 times x is equal to 0.6, 0.4. Actually, there is a name for this kind of case. This is called Markov matrix. Markov matrix has an eigenvalue equal to 1 and the other eigenvalue smaller than 1. These are, if the matrix satisfy this condition, it's called a Markov matrix. See, if it is a Markov matrix, then if you multiply the Markov matrix to any vector, okay, you will see that then this is 2 eigenvector of A, in the 2 eigenvector of A. So if you multiply by 1 time, it gives you this. The second time, remember, then I told you that the 0.6 and 0.4 does not change its length. Does not change its length. Does not change its length. However times you multiply by A. However, the other matrix will become 1/2. Becomes 1/2. Becomes 1/2. Becomes 1/2. Becomes 1/2. So that's the Markov chain. One of the eigenvector will disappear when you multiply any vector by A. That's the one of the eigenvector will become smaller, shorter and shorter and shorter, while the other vector will remain the same. So this is a simple example. When you multiply A to the 100 to 0.8, 0.2, then the contribution from the second eigenvector will diminish by 1/2 to the 100. You don't know how to calculate, right? But I know it's very, very small. Okay? So approximately, it could be put into 0. So the second eigenvector disappears when you do the A multiplication so many times to put it into very small number. However, the first eigenvector does not change because the eigenvalue is equal to 1. So you will remain there. So that means A to a large number times any vector, the answer is the same. 0.6, 0.4. In Chinese, 你的 A 的次方，只要你的次方是够大，它乘上任何一个东西，最后是一样的。任何一个，因为刚讲了，任何的一个 vector could be decomposed into 可以被分解成2个 eigenvector， 对不对？啊，你乘一次，其中一个就变小，再乘一次，再变小，再乘一次，再变小，所以你只要乘够多次的话，啊，最后的答案都是一样的啊。So A 的100次方 ，that means A to the 100 times anything will be equal to 0.6, 0.4. It does not just apply to the 100s. It applies to 200. It applies to 300. It applies to 1,000. So A, I could immediately tell you, A to the 1,000 times anything is equal to 0.6, 0.4. I can immediately tell you. A to the 1,000 times any x, not just this one. We only take this one as an example so that you can understand my argument. But x could be anything. A to the 1,000 times anything is equal to 0.6, 0.4. You can repeat the argument for any x. How powerful it is. So that's the power of eigenvalue formalism. Okay. It's okay. I personally think it's so powerful. Those mathematicians are good. So Markov chain, I'm not sure how we use it in physics. But remember this name. Sometimes I think it's in statistical mechanics, somewhere, Markov chain is very, very important. Not Markov chain, Markov matrix. When you multiply several times, it becomes a Markov chain. It becomes a step-by-step chain multiplication of this matrix. That's the first application. Please give me 10 minutes. I'll show you another application, which is called diagonalization of a matrix. Diagonalization of matrix. The formalism is very, very simple. It's very simple. Only take 2 pages. So be patient. But trust me, it's very, very powerful. Now, our matrix is A. Eigenvector A1 and A2. Eigenvalue lambda 1, lambda 2 as our usual notation. But now, let's compose a new matrix we call U. Don't ask why, but let's do it. Okay, for mathematicians, they can do anything without any motivation. So I put A1 as a column vector to the first column of the matrix. The second eigenvector is the second column of this 2x2 matrix. Is that okay? So if I write it out, it is A11, A12, and A22, and this is 1, A21 and A22. We could give it another name, sorry about that, but if I give it another name, I'll call it A11, A12, A21, A22, according to the standard notation of elements of a matrix. But anyway, that's the definition. I call this U. Remember, once again, the first column of this matrix is the first eigenvector. The second column of this matrix is the second eigenvector. Now, I multiply A and U. A times U will be equal to, write it out, A. And this is U, I just defined. And you know how to do it, right? When you do it separately. Because, for example, this times this will be upper left. This times this will be lower left. And therefore, it is just equal to A times A1, put it in the first column. And repeat, for the second column, it will be A times A2. Is that okay with everybody? It takes a little bit thinking, but it is true. In Chinese, 当我把这个乘的时候，我是把这个乘上这个放在左上角，这个乘上这个放在左下角。所以呢，这个 matrix 的左手边现在就变成是 A 乘上 A1 上面下面。Please convince yourself this is true. Second, it is this times this upper right. This times this upper and down lower right. So it is equal to A times A2. Why am I doing this? The reason is simple. It is lambda A1, lambda A2. Because A1 is the eigenvector of A. A2 is the eigenvector of A. Therefore, when you multiply A to A1, it is actually equal to a number multiply A1 and a number multiply A1. And it is easy to show the elements of this matrix is lambda 1, A11, lambda 1, A21, lambda 2, A12, lambda 2, A22. Show it yourself. This is equal to A11, A12, A21, A22, lambda 1, lambda 2, 0, 0. I can check it for you. This times this will be A11, lambda 1. Check. This times this will be A12, lambda 2. Check. Or you can check the other two. But this, what is this? The first matrix is just U. The second matrix is a diagonal matrix. Only have 2 elements in the diagonal. Yep.
Isn't the A1 times A2 cannot be the upper one?
Yes. I think we cannot multiply 1 times 2 matrix with 1 times 2 matrix.
I multiply a row with a matrix. These two elements I put in the first column.
No, I mean we cannot multiply a row matrix with a row matrix.
I can row matrix with, yeah, so that's why I multiply row with, oh, sorry. No, I haven't multiplied, and here, you mean here, right? This is a column.
A column. I mean, so I mean.
In here I just put in the elements.
We cannot put it like this.
Oh no, we are not multiplying.
So what
No, what I'm doing is just put the two elements of A1 here and here.
哦，所以 you're just combining
I
two
ju-
matrices.
Yeah, I should say I combine two columns into a matrix. I combine a two column vector into a matrix. The definition is here. Or if you prefer, this is another definition. So yeah, that's the correct way to say it. I combine two column vectors into a 2x2 matrix in this way. Don't ask me why, just because I can do it this way. Now I show you why I want to do this. Because then A times U equal to U times lambda. Why am I doing this? Take a look. If A times U equal to U times lambda, I can multiply both sides by U minus 1. Then you got U minus 1 times A times U. On the right hand side is U minus 1 times U equal to 1. So it's lambda. Ladies and gentlemen, I produce a diagonal matrix from A. The only thing it takes is to multiply U on the right hand side and U minus 1 on the left hand side. Okay, so it's powerful. U minus 1 times A times U is a diagonal matrix, and I know the elements of this diagonal matrix. Eigenvalue 1, eigenvalue 2. It's as simple as this, just one page computation. I can do it the other way. So, yeah, in Chinese, okay? I can do it the other way. I can multiply the same equation, again, AU equal to U lambda, what we just had got. I can multiply the equation, both sides on the right, by U minus 1. Then this will be AU U minus 1. Remember, U times U minus 1 is equal to 1. Let me write here. U times U minus 1 equal to 1. Also, U minus 1 times U is also equal to 1. So this is a standard definition of inverse matrix. Okay, and then if I multiply the right hand side by U minus 1, then U times U minus 1 equal to 1. So what do I get? On the left hand side is A times 1. Of course, just A. Okay, on the right hand side, U times lambda times U minus 1, it is this. So it is U times the diagonal matrix. This diagonal matrix consists of only eigenvalues as its elements times U minus 1. So I decompose any matrix into 3 matrices, and the information in these matrices are eigenvalues and eigenvectors. No more, no less. 任何的一个矩阵，我可以把它拆成3块。这3块呢，所有的资讯就全部是 eigenvalue and eigenfunction. So that's why I say if you don't tell me what the matrix is, I can immediately tell you hide the answer under your matrices. Okay? And you just tell me, I can ask you tell me the eigenvalue, you tell me the eigenfunction, eigenvector. I can just compose U by eigenvector and compose lambda by eigenvalue. I can tell you the answer under your matrix, under your bed. 假如我问你，你给我一个矩阵，但是你不要告诉我它是谁。但是呢，你回家自己去把它解出来， 它的本征函数、本征向量是谁？它的本征函数是谁？本征数值是多少？你告诉我本征函数向量就好，你告诉我本征值就好。我回来只要用这个公式一算，我立刻可以告诉你，你本来心里想的那个 matrix 到底是多少。Okay, so that's the power. Oh yeah, so here I showed you an example. Oh, the familiar 2x2 matrix that we have been using for several times, 0.8, 0.3, 0.2, 0.7. We know its eigenvalue, 1/2, right? Eigenvector, 0.6, 0.4, 1 minus 1. I can use it to form a U, a matrix. Then U times diagonal matrix times U minus is equal to this. So that's why I say, if in the beginning you did not tell me that this matrix is what in your mind, but you tell me the eigenvector is this, and the eigenvalue is this and this. Immediately I calculate this formula downstairs. I can tell you the matrix in your mind is this one. So that's what I say eigenvector in Chinese. 一个 maybe I don't have English translation. So the eigenvalue and eigenvector of a matrix is enough to represent the matrix. Okay. Oh, let me finish this page, and then we'll go. We'll be done today. So you may see. Okay, then that's great. Then what? Then what? Let me tell you how I can use this diagonalization. Here I got A equal to U lambda U minus 1. Then I can easily calculate A to the kth power. It is easy. A to the kth power, you just multiply the same A by k time. So it is U lambda U minus 1, U lambda U minus 1, U lambda U minus 1, you take it k times. But as smart as you can easily see that this long chain of matrices, when you multiply them, U minus 1 will cancel this. U minus 1 will cancel this. U minus 1 will cancel this. At the end, only lambda will survive. So it will be lambda, 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 lambda. So it's lambda to the kth power. But the first U will stay. The final U will, minus 1 will stay. So the answer is simple. A to the kth is equal to U lambda to the kth, U minus 1. And lambda to the kth, don't forget, lambda is a diagonal matrix. A diagonal matrix to the kth power is just lambda 1 to the kth power, lambda 2 to the kth power. So I got a so simple way to calculate A to the kth power. 各位同学，有没有感觉到这有多厉害？你告诉我一个 matrix， 如果你要我算 A 的 k 次方，你算不出来的。如果 k 是100，如果 k 是1000，你怎么算？对不对？现在我告诉你怎么算。因为 A 我就可以写成 U lambda U minus 1， 所以你乘个 k 次、100次、1000次都没有关系。重点就在于，当你乘起来了以后，里面的 U minus 1 U 会消掉啊。U minus U equal to 1. Therefore, this U minus 1 cancel out this U. Not cancel, I mean U times U minus 1 equal to 1. But 1 does not matter at all, so you can just get rid of it. Okay? So U minus 1 times U, U minus 1 times U, U minus 1 times U. All the U minus 1 times U becomes 1, and you can get rid of them. So eventually, only lambda will survive in the middle, so it will be lambda to the kth. But the first U will survive. The final U minus 1 will survive. So the answer is so simple. U times lambda to the k, U minus 1. Okay, so I got a formula to calculate A to the kth. Not only U to the kth. If you can define A to the kth, you can define the exponential of A. Oh, come on. What is exponential of A? What do you mean by that? A 的指数函数 ，A 是一个矩阵啊，the exponential of number I can understand. But what do we mean by an exponential of a matrix? But with our knowledge, it's so simple. Because we already know e to the 8th could be expanded into an infinite series. 指数函数可以拆成一个无穷级数， e 加上 a 加上 1 plus a squared over 2 factorial It applies when a is a number. It also applies when a is a matrix. Or I can take this as the definition of the exponential function of a. But still, it's not useful because this long chain of infinite series, you don't know the answer of it. Okay, if you don't have a way to compute it. But here, it gives us a way to compute it. Because here, a, u lambda u minus 1. A squared, answer is here. So u lambda to the second. I wrote it wrong. It's second, u minus 1. The third time, a cubed, u lambda to the cube, u minus 1. Okay, and I know the answer of this lambda squared, lambda cubed, because it is equal to the lambda 1 to the first, lambda 2 to the first, lambda 1 to the cube, to the square, lambda 2 square. So if you add them all together, it becomes exponential lambda 1, exponential lambda 2. The diagonal matrix times u minus 1. Well done. Okay, so what do we mean by e to the 8th? It means this formula. As long as you know the eigenvector, as long as you know the eigenvalue, you can define the exponential of the matrix. How powerful is that? Okay. 好，所以呢 I hope this give you some taste of how mathematicians are doing, what mathematicians are doing, and it's really, really powerful. Really powerful. Okay, next week when we come back, I'm going to prove 2 additional very, very important questions. The motivation actually are physics instead of mathematics. Remember, I told you, as you have already asked, our eigenvalue problem, A equal to lambda A, comes from our couple oscillation question. Okay? And the couple oscillation question, this A is written in this way. Okay? So it's the general matrix. Next week, I'm going to show you it is a symmetric matrix. You can check it yourself. It's symmetric. The point is, our solution is that when you solve the eigenvalue, the solution is eigenvector times exponential I omega t. But how could you be sure this omega is real? Remember, if this omega is not real, then this exponential I omega t becomes a exponentially decay function. So you better guarantee, or you better make sure the eigenvalues, this omega is real, or this lambda is positive. If not, you are in trouble. You see my point? Okay, let me put it in Chinese. Come on, 你解了半天了以后，你解出来的 eigenvalue 就是你的这个 exponential I omega t, of course. 如果你这个 omega 不是实数，你就完蛋了。假如你这个 omega 是 imaginary number, then exponential I omega t becomes exponential decreasing or exponentially increasing function. 它变成是一个指数递减或者是指数递增函数，你就完蛋了。Okay, so 你最好要能够确定这个 omega 是实数。换句话说 ，lambda 呢一定要是正的才行。Are you sure it's positive? Are you sure this lambda is positive? Yes, I'm going to prove to you. If this A is symmetric, this lambda, the eigenvalues, are always positive. That's what we are going to do next week. And it is so important, otherwise we cannot be sure we solved the couple oscillation already. No. After we've done this, we will be sure we solved the couple oscillation. See you next week, okay? Remember to turn in the homework. I'm going to have a lot of homework next week, maybe next time. OK， 好 ，about this 2x2 matrix。在接下来还会有一些有关于2×2矩阵的这一些讨论的那个习题，好，这时候就比较简单了，好，这比较简单，因为所有东西都是数学，好，你只要看懂了这些 PowerPoint 的话，应该不是对你太困难才对，好 ，OK，so see you next week. Have a good weekend.